Today's gate question is a unity feedback system that uses proportional integral control is shown in figure. The stability of the overall system is controlled by tuning the PI control parameters Kp and Ki. The maximum value of Ki that can be chosen so as to keep the overall system stable or in the worst case marginally stable is. What is the problem? This is the feedback system with proportional and integral control. You have to find the maximum value of Ki for which the system is stable or at least marginally stable. We can solve this by using RH criteria. So now we'll solve it. Okay. So we can use RH criteria to solve this problem. Okay. In the RH criteria, the first point is you have to form Routh array. You have to go for characteristic equation. What is characteristic equation? 1 plus g of s into h of s is equal to 0. Here as the feedback is unity, h of s is 1. And what is g of s? G of s is the product of these two. So implies 1 plus Kp plus Ki by s into 2 by s cube plus 4s square plus 5s plus 2 is equal to 0. That implies 1 plus skp plus ki by s into 2 by s cube plus 4s square plus 5s plus 2 is equal to 0. Yes, simply you take the LCM and just multiply for 1. Yes, s power 4 plus 4s cube plus 5s square plus 2s plus this 2 and this skp plus ki, 2s kp plus 2 ki is equal to 0. We'll do simplification. S power 4 plus 4s cube plus 5s square plus 2 plus 2 kp of s plus 2 ki is equal to 0. So now this is the characteristic equation. Now you have to form Routh array. Consider the characteristic equation. S power 4 plus 4s cube plus 5s square plus 2 plus 2 kp of s plus 2 ki is equal to 0. Now form the Routh array. S power 4, s cube, s square, s or s power 1 and s power 0. Okay. Now write this coefficient, s power 4 coefficient here, it is 1. And next you have to write the alternative terms in a row. So next is 5. Next is 2 ki. So in this row, the next term is s cube term. First you have to write the s cube term. S cube coefficient is 1. And then s 2 plus 2 kp. Then fill your Routh array. To write the term here, just do 4 into 5 minus 1 into 2 plus 2 kp by 4. 4 into 5, 20 minus 2 plus 2 kp by 4. Total it is 18 minus 2 kp by 4. To write the term here, 4 into 2 ki, 8 ki, it is 0 here. So 8 ki minus 1 into 0, 0, 8 ki minus 0 by 4, it is 2 ki. Again, to write the term here, follow the same procedure. This product minus this divided by this, so it is 18 minus 2 kp by 4 into 2 plus 2 kp minus 8 ki divided by 18 minus 2 kp by 4. Put this term, this column term, this term, this is 0 because this is 0 and this is 0, so it is 0. So now we know for overall system stability, first column of the Routh array must be non-zero. Okay. So by taking that, just you take these two terms. First take 18 minus 2 kp by 4 must be greater than 0. System stability. For system stability implies 18 minus 2 kp is greater than 0. This implies kp is less than 9. Okay, then take another term. 18 minus 2 kb by 4 into 2 plus 2 kp minus 8 ki by 18 minus 2 kb by 4 must be greater than 0. Implies 18 minus 2 kp by 4 into 2 plus 2 kp minus 8 ki is greater than 0. 18 minus 2 kp into 2 plus 2 kp minus 32 ki is greater than 0. If you do further analysis, 36 plus 32 kp minus 4 kp square minus 32 ki is greater than 0. So implies 36 plus 32 kp minus 4 kp square must be greater than 32 ki. Implies ki is less than 36 plus 32 kp minus 4 kp square by 32. To get a numerical value, let us take kp equal to 9 and I'll see what is ki. If kp is 9, get the value of ki. So just substitute 9 here. 36 plus 32 into 9, 288 minus 9 square into 4, 324 by 32, that is 0. So what is the conclusion here? When kp is 9, ki is 0. But this is proportional integral control. The value of kp and ki will control the feedback system. So, but at Kp equal to 9, we are getting Ki of 0. But the actual condition is Kp is less than 9. So, to find the value of Ki or the maximum value of Ki at which the system is stable, you have to go for, the other alternative is you have to go for dki by dkp is equal to 0. So, this is to get the maximum value of Ki, which makes the system stable, and that depends on the value of Kp. Take the Ki expression. 36 plus 32 Kp minus 4 Kp square by 32. Then to get the maximum value of Ki for system stability, dki by dkp equal to 0. So, you have to do the differentiation of Ki with respect to Kp. You will get 32. Yes, here is Kp and Kp square. So, 32 minus 8 Kp is equal to 0. Implies 8 Kp equal to 32 implies Kp is equal to 4. Okay. So, now substitute Kp equal to 4 in Ki expression. I will get Ki equal to 36 plus 32 into 4 minus 4 into 4 square by 32. 36 plus 128 minus 64 by 32, which is nothing but 100 by 32. The answer is 3.125. Okay. So, now this is the maximum value of Ki at which the system is stable. So, what are the values of Kp and Ki for the system stability? Kp equal to 4 and Ki equal to 3.125. Okay. Here, actually from the Routh array, the conditions are Kp must be less than 9 and Ki must be less than this 36 plus 32 Kp minus 4 Kp square by 32. So, we checked for Kp equal to 9. So, if Kp is 9, Ki becomes 0. Just substitute Kp and Ki here. Suppose Kp 9, you will get 0 here. Ki 0, you will get 0. And even if you keep Kp and Ki 9 and 0, you will get 0. So, all the first column of Routh array are becoming 0. Fine, that is the condition for marginal stability. But even you have to check whether there exists any other value that can give overall system stable. So, for that you have to check dki by dkp. For that you have to do dki by dkp equal to 0. So, with that process we got Kp equal to 4 and Ki equal to 3.125. So, if you substitute Kp equal to 4 and Ki is 3.125, yes, all this first column of the Routh array are non-zero with no sign change. So, the system is said to be stable. So, the system is said to be stable for the values Kp equal to 4 and Ki is equal to 3.125. So, here the answer is 3.125. Thank you for watching this video. If you like this video, please don't forget to like, share and subscribe.